iconic structure you see. Every metro line, every skyscraper, every bridge that connects lives rests on a silent foundation. A foundation that begins deep beneath the surface. And that's where we come in. Cengrs Geotechnica, smart geotechniques for better foundations.
Namaskar. My name is Sanjay Gupta. Thereafter, right from 1971, I was employed in a job and as a site engineer. Then I became a soil engineer, then senior engineer, and likewise. As a young, enthusiastic engineer with a passion in geotechnical engineering, started as an entrepreneur, found Cengrs, commonly known as Cengrs, that's Foundation Engineers. Cengrs is now 35 years young with a vision to make geotechnical practice as a specialist engineering services. Cengrs has been instrumental in upgrading the code of practices to improve geotechnical practice in the society with an effort to match with international practices. Geotechnical engineering is a science, but it's practice an art.
I always believe and say, be a part of soil, be it soil, feel the stresses, deform along with it, solution shall emerge within itself.
Cengrs was built on a commitment to generate authentic geotechnical data, maintaining technical integrity and a deep sense of purpose. Over 3.5 decades, we've partnered with India's most ambitious infrastructure projects, laying the groundwork, literally, working for a stronger tomorrow.
I'm Ravi Sundaram, Director of Cengrs Geotechnica Private Limited. At Cengrs, we are not just offering services, we are offering quality engineering. Our NABL accredited lab, our ISO certifications, our advanced testing equipment. From soil investigation to foundation testing, each step is backed by thorough and rigorous quality assurance so as to ensure the quality of data is trustworthy. Over the last 35 years, we have been building this trust with our clients and in professional circles.
Be it a metro line, a smart city, or a high-rise, our detailed, data-driven approach ensures safe, economical, and sustainable construction. It's not just about what's underground, it's about what that foundation enables above the ground. Behind every data point is a human being. Our people are the foundation of Cengrs. From seasoned engineers to young interns, every mind here is tuned to solve challenges and deliver value. We don't just work for our clients. We test today for tomorrow's progress. And as the nation progresses, we take pride in our contributions to the projects executed and humble achievements.
Hello, I'm Saurabh Gupta, Director at Cengrs Geotechnica Private Limited. As the market leader, we have decided to transform the geotechnical engineering industry in India and bring it to world-class standards. To do this, we have implemented a system-driven approach so we can deliver consistent quality and on-time delivery for our customers. We are the first ones to bring in latest ground technologies such as cone penetration test, pressure meter test, cross-hole seismic tests, etc. so we can unlock value and mitigate project risk. As always, smart geotechnics for better foundations.
From the surface, it's just soil. But to us, it's the beginning of possibility. Cengrs Geotechnica, smart geotechniques for better foundations.
Good morning, everyone. Welcome to Cengrs webinar series and thank you for joining with us. I am Manju Mehra, Marketing Coordinator at Cengrs, and I will be your host for today's webinar on implication of IS 1893-2025 geotechnical aspects. Today's session will focus on the key geotechnical implications of IS 1893-2025, including VS-based site classification, investigation depth, PGA-based seismic inputs, liquefaction assessment using SPT, CPTu, and shear wave velocity, with reference to the latest code provision. We are pleased to have two speakers with us today, Professor Ravi Sundaram and Dr. Abhishek Sakleshpur. Our first speaker, Professor Ravi Sundaram, is the director of Cengrs Geotechnica Private Limited, with over 44 years of experience in geotechnical investigation and allied field. He is also serving as a professor of practice adjunct faculty at IIT Jammu, and he is an active member of BIS, RIC, and many others committees. Our second speaker, Dr. Abhishek Sakleshpur, is the geotechnical engineer and at Cengrs with PhD from Purdue University in USA, and he has an extensive experience in CPT, foundation system, and geotechnical research. With this, we will begin today's webinar with Professor Ravi Sundaram. Over to you, sir.
Okay, Ravi sir will join us in a little bit. In the meantime, I'll get started with the presentation. I hope my audio is coming through. I hope my slides are visible.
Hello, can you hear me now?
Oh, yes, sir. We can hear you.
Oh, you can?
Yes,
all
we
right.
can hear you now.
Can I now present?
Sure, sir. Go ahead.
Can you hear me now?
Yes, sir.
Great. Sorry for that small blip. I welcome you all to the first webinar in 2026 organized by Cengrs. The IS 1893 Part 1 has recently been released in November, and this code has brought several changes both in the geotechnical and structural design aspects. So today we will be talking about the geotechnical aspects of this new code. So the topics which are covered here are the changes in IS 1893 Part 1, 2025, the site investigation considerations. You have the site classification and minimum depth of investigation required for performing a geotechnical investigation which covers the seismic aspects. Then the liquefaction susceptibility assessment. There has been a change in the earthquake zones, introduction of a return period and peak ground acceleration requirements, and then the estimation of CSR and CRR, as well as the factor of safety. Now the analysis is based, SPT-based analysis is based on Bollinger and Idris 2014. Also the CPT is based on the same publication. The VS, of course, is the same as in the NCER 2001. So the factor of safety is required now been increased from 1.0 to 1.4, and as such, there has been a substantial impact on this. We should be explaining this through three case studies. One, a tall building in Gurgaon, a wind turbine in Gujarat, and a bridge in Assam over river Brahmaputra. I would start by introducing Cengrs to you. We have been in the field of geotechnical consultancy, investigations, and all since 1990. We have over 150 members team. We have over the years published over 85 papers, done up 200 to 250 projects annually, and we are close to 7,000 projects in the Indian subcontinent with over 1,500 satisfied customers. So our primary activities include geotechnical investigation, geophysical surveys, geotechnical laboratory testing, engineering consultancy, topographic and hydrogeological surveys, foundation testing, etc. So our intent is to provide complete solutions, 360-degree solution as we call them. So as a geotechnical investigation agency, we provide accurate data, reliable data for foundation analysis. We have in-house strength and capability for performing foundation analysis, as well as extensive experience to do these studies. Foundation testing, quality assurance, and quality control. This is one very important aspect. This includes review of the technical specifications, foundation instrumentation, data analysis, site visits, in-house capability for pile testing, etc. And of course, as a consultant, we have a strong technical backing with various software which we have been using, etc. NABL has accredited us. We are the first geotechnical engineering testing laboratory to be accredited by NABL. So we do a host of various lab tests and as well as field tests. We have a pan-India presence. You can see the various projects done in different areas of the country. Now I go straight on to IS 1893 2025, sorry. So introducing this code to you, it is a earthquake resistant design is the most critical aspect of both geotechnical and structural engineering. And as you know that 75% of India's population is in seismically active regions, and 59 to 61% of the landmass is under seismic risk. It has been 200 years since any major earthquake has occurred in the central Himalayas. As a result, we have to be aware that there could be earthquakes anytime. So this code represents a paradigm shift in the seismic design philosophy. It reflects an important transition towards safer, smarter, and performance-oriented seismic design. So based on the updated seismic hazard studies, it offers a more realistic representation of the earthquake forces across India. It aligns India to the global practices and the practices which are used internationally. So we can call this a responsible seismic design. Don't treat it as an over design. Sometimes people do tend to think that since the requirements have increased, so it is an over design. The intent is not to make everything stronger and safer, but to ensure that essential buildings remain functional even after major earthquakes. It adds an extra safety net, equipping buildings to better withstand the seismic events through strengthened provisions. So you can make sure that even if there is a major seismic event, your structure is better ready to function even after the major earthquakes. So if we were to look at the key highlights, a new earthquake map, earthquake zone map has been released. This is a revised and more accurate seismic zone map, and it has been introduced using advanced probabilistic hazard assessment, PSHA as it is called. The minimum geotechnical investigation depth has been defined. So it specifies that the minimum depth of foundation should be 2 times the width of the foundations for mats or raft foundations, spread footings, and as far as pile groups go, the length of the pile plus 2 times the width of the group. So soil exploration must go deeper. A generic 10 or 15 meter deep boreholes won't suffice anymore. So investment in good geotechnical investigation is now important. So the site classification is now based on VS, not on N values. So SPT-based classification has been replaced by shear wave velocity classification. Sites, it is classified A to E. So this means that geophysical testing for shear wave velocity determination has become mandatory. So you could do the shear wave velocity determination using seismic cone penetration test or cross-hole seismic test or downhole seismic test. So this is now required. If you are in site E, site class E, ground improvement and post ground improvement verification is mandatory. Now, geotechnical considerations have been strengthened. So there is a revised liquefaction assessment, soil flexibility effects, that is the soil structure interaction, and site-specific spectra provisions. Now these have been added. The Gmax degradation curves based on shear strength and plasticity index are provided. You have a requirement for site-specific earthquake hazard assessment. So this should be done when the project site for the project site, when your structures rest on sites site class A to D with design return period of 2,475 years, or in site class E for all cases. And higher importance has been given, higher safety factor for important structures. So hospitals, schools, government buildings, bridges, pipelines, industrial structures get higher return period, so that it has to be designed more safely. Let's make a comparison of 2016 code versus 2025. In the 2016, shear wave velocity measurement was optional. Now it is mandatory for specific special critical structures in all earthquake zones and important structures in zone 4, 5, and 6. The N60 VS correlation may be used only for normal structures in all earthquake zones and important structures in zones 2 and 3. Otherwise, you have to measure the shear wave velocity. The site class assessment was based on a weighted average of the SPT values in 2016 code. Now you have to take a weighted average of shear wave velocity within the depth of influence of the foundation, which is 2B below the foundation. The 2016 code had 4 zones, 2, 3, 4, and 5. Now the zoning map has been updated to 5 zones with a new zone 6 being introduced. The earthquake magnitude in the 2016 code, it does not directly specify what should be the magnitude of earthquake to be considered for each zone, whereas now we have very clear definitions. For zone 2, you use 6, 3, you use 6.5, and so on, and zone 6, you are going to use 8 on the Richter scale. The seismic zone factor, or the peak ground acceleration A max by G, the 2016 code gave fixed values, 0.1 for zone 2, 0.36 for zone 5. Now this will depend on your design method, whether it is limit stress, limit state, or working stress, and also the return period of the earthquake. Importance factor in 2016 code, there was no such provision. Broader and strictly enforced categorization has been provided in the 2025 version, particularly for lifeline infrastructure, bridges, hospitals, schools, public structures, etc. Now, seismic bearing capacity, there was no provision, but now new bearing capacity factors have been provided for the seismic case. SPT-based liquefaction analysis, it was based on the 2001 Youd and Idris method. Now it is the Boulanger and Idris 2014 method. Similarly, the CPT, also based on Boulanger and Idris. The VS-based analysis, of course, it's the same as 2016 code. The DMT-based liquefaction analysis, there was no provision in the IS 1893 2016. In the 25 code, we have the new method proposed by Robertson, so that has been proposed. Liquefaction triggering criteria, in the 2016 code, you had factor of safety less than 1 liquefiable and greater than 1 non-liquefiable. Here, it has a slightly more complex definition. A factor of safety less than 1.2 is unsafe, greater than 1.4 is safe, and if it is between 1.2 and 1.4, you must estimate the ground settlement resulting from the earthquake loading. The figure 7 of the new code is based on Zhang et al. 2002 method, so this has to be done. If we were to look at the site investigation considerations, for normal structures in earthquake zones 1 to 6, you can use corrected SPT values and VS profiles if available. For important structures in zones 2 and 3, you may use VS profiles if available, and they are preferred over the corrected N values. But in zones 4 to 6, you need VS from geophysical investigation. Similarly, for critical and special structures, VS is required from the geophysical investigations. A minimum depth of investigation, this is very important. Now, the new code says that if B is the smaller planned dimension of the foundation, for mat foundations or raft foundations, your depth of investigation should be 2B below the foundation. For piles, if it's a single pile, it is depth of pile plus twice the diameter of the pile. If it's a pile group, which would normally be the case, then you must take the plan area of the pile group, the smaller dimension, and twice that dimension you have to investigate below the pile tip. So now your site class assessment. There is a correlation given in the code for computing VS on the basis of N values. But this, as I told you, you can use it only in zones 2 and 3 or normal structures in zone 4 to 6. But otherwise, you must be doing the VS assessment. The classification A, B, C, D, E is based on the shear wave velocity, which is given in this table. So approximate shear wave velocity you can estimate based on N values, but only under limited conditions. So if you were to look at the equivalent N values for the various classes, site class A, you have N values more than 100, as same for BR for class B. For class C, dry sands, it is 20 to 100, more than 43 for saturated sands. Class D, you can have lower N values, dry sands 5 to 20 and saturated sands 8 to 43, and clays 15 to 100. But where the N values are less than 5 to 15, it would be class E soils. So the N60 derived VS is permitted only under limited conditions in zone 2 and 3. Direct measurements of VS are always preferred as explicitly stated in the code. The N60 to VS correlation is not applicable when N is less than 10. In such case, VS has to be measured. Unrealistically high N60 values for stiff to hard clays may be due to the empirical correlation, so be aware of that. So be careful in doing your liquefaction analysis. So how to determine VS? There is the seismic cone penetration test, cross-hole seismic test, seismic flat dilatometer, downhole seismic test, suspension logging. You can see the various tests which are used commonly. There are also the non-invasive techniques like MASW, SASW, seismic refraction, passive surface waves, and various others like REMI and all that. Many of these are very much used in the country, and you may prefer, particularly for deep investigations, you may want to do with cross-hole seismic test. If you're not getting refusal, you could go with seismic cone penetration test. MASW, SASW, of course, they are very useful tests. So just a brief look at cross-hole seismic test. So you have 3 boreholes, and one borehole you create the impact, and the adjoining 2 boreholes you receive the waves. This way you are able to get a continuous profile of P wave velocity and shear wave velocities, and thus determine the various dynamic parameters. And then you can do your site class determination, your seismic analysis, static analysis, etc. The seismic cone penetration test, very effectively used. You have 2 sensors and an inclinometer. So you create an impact by horizontally hitting this source, and from the arrival of the wave, you can work out the seismic wave velocity. So this is the equipment, the seismic, the cone penetration test pushers. We have been using this quite extensively. We have 5 of these rigs, and this is a hydraulically, it's a crawler mounted rig. So the advantage is that it's quite fast. You can do 30 meters in just less than half an hour. In granular soil, you get continuous and near continuous data, accurate, very reliable, enhanced, good quality data, with very good repeatability. It's versatile for the wide spectrum of CPT-based geotechnical parameters and for foundation analysis. In soft soils, you can even go up to 100 meters, but even in medium to stiff soils, you could probably go 40 meters even more. It's very reliable, repetitive data, and irrespective of who does the test, you get the similar results because it is digital data acquisition. You could do sampling with discrete soil sampling using CPT samplers, also called the MOSTAP sampler. It can be coupled with various sensors to get hydrostatic pressure, shear wave velocity, inclination, thermal resistivity, vision cameras, etc. No hammers or rotating parts. It's clean, no drilling mud. Cost effective. Testing is not much more expensive than conventional boreholes, so it's almost the same cost. Similar kind of the kind of data that you get, you can compare it with the shear wave velocity interpreted from the conventional CPT as well as measured from the seismic CPT. You see such a good comparison here. It's very versatile test. You get a whole lot of geotechnical parameters, right from permeability to consolidation parameters, soil classification, etc. Now we start with the discussion on liquefaction susceptibility assessment, which will be presented by Dr. Abhishek. So Abhishek, may I request you to take to the stage?
Sure, sir. Let me share my screen. I hope my screen is visible, sir. Is my screen visible?
Yes, it is.
Okay. So let's move into liquefaction susceptibility assessment. So first, just a few fundamentals. So liquefaction, as we know, refers to the complete loss of shear strength and stiffness of loose, saturated, silty fine sand to sandy silt kind of materials below the water table due to the buildup of the excess pore pressure during a seismic event, with the consequence that your effective stress drops to zero and your soil essentially becomes like a liquid. Now, in the IS code, clause 5.1 is important because it states that the site selected to construct the structure shall neither liquefy nor slide during the design earthquake shaking specified in the standard. Provisions for liquefaction susceptibility assessment are provided in clause 9.2, and we'll go over that in the following slides. Also important to note that as per the IS code, a site which is likely to liquefy shall not be considered as a potential site unless suitable remedial measures or ground improvement techniques are adopted. So this slide compares the earthquake zone map between the 2016 version of the code and the new 2025 version of the code. So in the 2016 code, we basically have 4 zones, zones 2, 3, 4, and 5. Whereas in the new code, we have an additional zone 6. Now, the states that fall in the seismic zone 6 include Jammu and Kashmir, except the northeastern part of the state, Himachal Pradesh, except the southern part, Uttarakhand, all the northeastern states, Sikkim, Arunachal Pradesh, Assam, Nagaland, Manipur, Mizoram, Tripura, Meghalaya, Western Gujarat, particularly Bhuj and Kutch, and finally the Andaman and Nicobar Islands. So it's important to know the risk, be prepared, and to stay safe. And the way we can do that is by following updated building codes, conducting site assessments, earthquake preparedness, and community awareness and training. Now, in terms of the earthquake magnitude on the Richter scale, so for zone 2, it starts from a value of 6.0, increasing up to a magnitude of 8.0 for earthquake zone 6. When we do the liquefaction susceptibility assessment, one of the things that we need to consider is the category of the structure. Now, IS code defines 4 categories of structures: normal structures, important structures, critical structures, and special structures. And this classification depends on the relative severity of the negative consequences, that is, loss of life and livestock, loss of property and harm to natural environment in the event of the failure of the structure. Now, apart from the IS 8093 Part 1, there are other parts going from Part 2 to Part 11, and each of these parts focuses on different types of structures, such as liquid retaining structures, bridges, industrial structures, buildings, base isolated buildings, long distance pipelines, steel towers, coastal structures, tunnels, and earthen embankments and earth retaining structures. Now, in order to determine the peak ground acceleration, we need to know what is the design return period. Now, in the new IS code, there are 2 tables to estimate the design return period. Table 1 that you see on the slide here is the return period to be used in the design of different categories of structures that are designed by the limit state method. And you can see in the table, depending on whether it's a special structure going all the way down to a normal structure, the design return period is different. So for a normal structure, it's 475 years. And as you go to a special structure, the design return period increases to 4,975 years. Now, table number 2 is for the design of different categories of structures by the working stress method. the return periods that you see in this table are lower when compared to the limit state method, ranging from 175 years for normal structures up to 975 years for special structures. Now, a question that often comes up is which table should we use for liquefaction analysis? Is it table 1 or table number 2? Now, if we refer back to the clause 5.1 that you saw earlier, so this clause is a shall clause, making it a mandatory requirement. And to repeat that clause, it says that the site shall neither liquefy nor slide during the design earthquake shaking. What that means is basically the structure must not collapse under the design ground shaking. Now, if we choose to use table 2 for liquefaction susceptibility analysis, there is an incompatibility because although the code directs working stress method designers to table 2 for structural design and structural member proportioning, however, for liquefaction analysis, the higher hazard levels in table 1 should be prioritized. And this is because if you look at liquefaction, it's a geotechnical ultimate limit state that leads to the collapse of the entire structure. And you could have a situation where a site may pass table 2 shaking, but it could liquefy under the return periods in table 1, which would then violate your clause 5.1. So what is your way forward? Use your table 1 return periods, which represent the 475 year to the 4,975 year collapse prevention level, so that the site will remain stable under the intensity of the design earthquake shaking. And the site will be robust enough to handle the design level shaking, regardless of whether the superstructure is designed using working stress method or limit state method. So to summarize the previous slide, for working stress method, structural design, use your table 2 to get the design return periods. For limit state method design of structures and liquefaction susceptibility assessment, use the return periods given in table number 1. And by doing so, we ensure that we do not violate the mandatory shall not liquefy provision of clause 5.1, making our design fully consistent with the safety objectives of the IS 2025 code. So let's look at a few cases. So if we take buildings, for example, so buildings have a separate part, which is part 5 of the IS 1893 code. And nowadays in India, we see a lot of tall buildings and high-rise residential towers that are coming up. So for residential or commercial buildings with occupancy more than 100 people or tall buildings, these buildings are classified as important buildings according to part 5 of the IS 1893 code. And the design return period for liquefaction susceptibility analysis is 975 years. Similarly, if we go to bridges, which is covered in part 3 of the IS 1893 code, if we take a river bridge or flyover bridges inside cities or bridges on national and state highways, these fall under the category of important bridges. However, if you have a long bridge that is more than 1 kilometer length across perennial rivers and creeks, or bridges for which alternative routes are not available, then these are classified as critical bridges according to the IS code. And so we choose the design return period accordingly. Now in this table, you can also see that there is a column with the importance factor. So what is this importance factor? It's important to note that the importance factor is not used to calculate the P-ground acceleration for liquefaction susceptibility analysis. This importance factor is a structural parameter that's used to determine the design earthquake force for the structural elements themselves. Whereas the PGA for liquefaction susceptibility analysis is governed by the seismic hazard of the site. I is used specifically to estimate the design horizontal acceleration coefficient and the resulting design base shear for structural design. And it accounts for the functional use of the structure and the consequences of its failure. Example, lifeline infrastructure such as hospitals or major bridges require higher design forces, and they are given a higher importance factor. So to summarize, for liquefaction analysis, the primary seismic parameter is the peak ground acceleration, which is based on the zone factor for a specific design return period TR. And the importance factor is not used here. Whereas for structural design, the primary seismic parameter is the design base shear, which depends on the zone factor, the importance factor, and an elastic force reduction factor R. So once you know the earthquake zone, that is zone 2 to zone 6, and your design return period, we can then use table 3 of the IS code to obtain the peak ground acceleration. So as an example, if we are in Delhi NCR, which falls under earthquake zone 4, and if you take a tall building, for example, which has a design return period of 975 years, then your peak ground acceleration is 0.28 g. This table summarizes the earthquake magnitudes and PGA for a few select cities in India. So if we look at Chennai, for example, in the 2016 code, it was in zone 3 with magnitude 6.5, PGA 0.16 g. In the 2025 code, it falls in the same zone, same earthquake magnitude, but the PGA ranges from 0.13 to 0.33, depending on the design return period. Kolkata, on the other hand, has been upgraded from zone 3 to zone 4 in the new IS code, and so the PGA values are also higher. Delhi NCR, same zone 4 in the new IS code. PGA values depend on the design return period. Now, the new zone 6 that we saw earlier, it includes Bhuj and Guwahati, which now have much higher design earthquake magnitudes and higher values of PGA, depending on the return period. So let's move to estimation of cyclic stress ratio, CRR, and factor of safety. I'll briefly go over the following slides in the interest of time, but the equations are extensively covered in the IS code. So cyclic stress ratio represents the seismic demand, and it depends on the peak ground acceleration, the vertical in situ total and effective stresses, and the stress reduction coefficient RD. The stress reduction coefficient takes into account the earthquake magnitude M. Now, once you have the cyclic stress ratio, we then need to estimate the cyclic resistance ratio, which represents the resistance to liquefaction. So CRR is equal to the value of CRR for a 7.5 magnitude earthquake under a vertical effective stress of 100 kPa, multiplied by the magnitude scaling factor and K sigma, which is an overburden stress correction factor. Now, depending on whether we use the standard penetration test SPT or the cone penetration test CPTu or shear wave velocity, we estimate the CRR for a 7.5 magnitude earthquake. The CPT-based method in the new IS code is based on Bullinger and Idris 2014. So CRR for a 7.5 magnitude earthquake is given by the equation here. The key parameter is QC1 NCS, which is a clean sand equivalent stress normalized cone resistance. It includes the stress normalized cone resistance QC1 plus a delta QC1, which takes into account the effect of fines content. The equation to calculate the fines content is given here at the bottom of the slide. And this equation for the fines content has the soil behavior type index IC, which depends on your normalized cone resistance and the normalized friction ratio. And it also has a fitting parameter CFC, and the IS code suggests a default value of minus 0.07 for this parameter. And the other equations on the slide are for the normalized cone resistance and the normalized friction ratio. Moving to the SPT-based method, which is also based on Bullinger and Idris 2014. Here the key parameter is N160CS, which is the clean sand equivalent stress normalized SPT blow count corrected for 60% energy transfer. So N60, as you know, has your field SPT-N value, Nm, that is multiplied by a set of correction factors. So CS accounts for the presence of a liner in the split spoon sampler. CB is a correction factor for borehole diameter. CR is a correction factor for rod length. And the CE is a correction factor for hammer energy that we get when we do SPT analyzer tests in the field. Cn is a correction factor for the overburden pressure. Notice here there's a small typo in the equation. So N160 doesn't include or should not include the correction factor Cn because it is already reflected above in the equation to calculate N160. The parameter delta N160, similar to the CPT-based method, includes the effect of fines content. Here the fines content can be determined directly from boreholes by conducting laboratory sieve analysis and hydrometer analysis. Now in the shear wave velocity VS-based method, this is based on the NCWR 2001, similar to the 2016 version of the IS code. Here the key parameter is VS1, which is a stress-corrected shear wave velocity. And we also have another parameter, VS1 star, which is a limiting upper value of VS1 for liquefaction occurrence. And this parameter accounts for the effect of fines content. Now, the factor of safety against liquefaction is the ratio of CRR to the CSR. And as Ravi sir mentioned previously, the factor of safety against liquefaction, if it's less than 1.2, then the soil layer shall be considered unsafe against liquefaction. If it's more than 1.4, the soil layer may be considered safe against liquefaction. And between 1.2 and 1.4, the resulting liquefaction-induced settlement should be verified based on figure 7 of the IS code. And this is that figure to calculate liquefaction-induced settlement. So in this figure, safety against liquefaction, and on the vertical axis is the post-liquefaction volumetric strain in percentage. Notice that you have 7 different curves. Each curve corresponds to a different value of relative density, starting from 30%, corresponding to loose sand, for example, going all the way to 90% corresponding to very dense sand. Each case also corresponds to a different value of N160 and a different value of QC1N, as summarized in the table here. So case number 1 would lead to higher post-liquefaction volumetric strains as expected. And as you go down to case number 7, you have lower post-liquefaction volumetric strain. Once you get the epsilon V, you have to multiply that with the thickness of the soil layer. And if you then take the summation of this across the zone of influence of the foundation, for example, you then get the total liquefaction-induced settlement. So let's look at 3 case studies to illustrate the application of the provisions in the new IS code. The first case study is a tall building in Gurgaon, Haryana. So this tall building includes 3 high-end towers, which are 140 meters in height. Each tower has 4 basements for parking and associated services. In addition to the 3 high-end towers, we have 4 low-rise blocks with 4 basements and 7 floors each. The plot area is approximately 10 acres, and you can see an architect's visualization of the towers on the figure here. The scope of work in this project included 9 boreholes to 65-meter depth, 8 boreholes to 35-meter depth, 3 SPT analyzer tests for SPT energy measurement, 18 CPTUs to 30-meter depth, 3 seismic cone penetration tests to 30-meter depth, and also pressure meter tests in 3 boreholes to 65-meter depth. So this would represent what we call as a gold-level geotechnical investigation for accurate site characterization and enhanced liquefaction susceptibility assessment and foundation design. So this is a plan of the field investigation. So you can see the 3 towers here in plan view and the layout of the boreholes, CPTUs, seismic CPTUs, and pressure meter tests. On the right-hand side are a few photographs of the field work in progress. And for this presentation, we'll focus on tower number 3. So here we can see the summary profiles of the site from boreholes and CPTu interpreted soil profiles. So basically the soil profile consists of silty fine sand from the existing ground level to about 7.5 meter depth. This is underlain by sandy silt of low plasticity to the final explored depth of 65 meters. Groundwater was met at a depth of about 13 to 14 meters at the time of the field investigation. In this slide, we can see the results of the SPT energy done for tower number 3, and the average energy transfer ratio was found to be 70%. So what that means is you have to correct your field measured SPTN value by multiplying it with the energy correction factor. So to get N60, you multiply your field N value with the ratio of 70 divided by 60 to get the corrected N60 value, corrected for energy transfer. Here we can see the results of the cone penetration tests. So the plot of cone resistance with depth. The CPTu soundings were terminated at a depth of about 27 to 28 meters due to refusal. But for a foundation design, what we did was we extrapolated the cone resistance with depth based on the trend of the SPTN values in order to do the foundation design. Then we also have plots of sleeve friction, pore pressure, and shear wave velocity. So the black solid line is the interpreted shear wave velocity from CPT correlation, and the scatter points that you see are the measured shear wave velocity from the seismic cone penetration test. Notice that the measured values of shear wave velocity are slightly higher than the CPT interpreted values using correlation, and we will see why this is the case in the following slide. Finally, we have the CPTu interpreted soil behavior type. So in the upper profile up to about 7.5 meter depth, we can see the presence of sandy silt transitioning to silty fine sand in the lower half of the profile. Now, in addition to the measured parameters, we can get a host of other parameters that are interpreted from CPTu results. So first is the CPTu interpreted N60, which is the black solid line that you see on the plot. And we have overlaid the measured values of N60 from the 3 boreholes. And we can see that there's a reasonable match between the CPT and the borehole results. The next plot is bulk unit weight interpreted from CPTu and laboratory determined values of unit weight, also in good agreement. Undrained shear strength, CPTu interpreted values, and measured in the laboratory from UU triaxial tests, also showing a reasonable match. Friction angle determined from direct shear tests in the laboratory, CPTu interpreted values, constraint modulus, and finally the small strain shear modulus from CPTu and from the seismic CPTu. Now, we had done 3 seismic cone penetration tests, one for each of the 3 towers, and we can see that the repeatability of the test and the consistency in the shear wave velocity is quite good across the 3 seismic cone penetration tests. Notice that there's a general trend of increasing shear wave velocity with depth. Similarly, with the small strain shear modulus that is determined from the shear wave velocity through elasticity theory. The plot on the right-hand side that you see is a plot developed by Professor Peter Robertson. On the x-axis, you have the small strain rigidity index, which is the ratio of the small strain shear modulus G0 divided by the net cone resistance. And on the y-axis is the normalized cone resistance. Now, most of the data points, or all the data points from the seismic cone penetration tests, plot above this upper bound line, represented by a normalized rigidity index, Kg star of about 330. So what that means is when the data points plot above this line, it indicates that the site is aged, or it indicates the presence of natural cementation or microstructure in the soil profile. And this is a direct consequence of the higher values of shear wave velocity that we obtained from the seismic cone penetration test compared to CPT interpreted correlations. So one of the features of the seismic cone penetration test data is that it can be used to identify natural cementation in the field, soils with significant aging and microstructure. Now, for site class assessment, as per the new IS code, the 140-meter high towers were planned with 4 basements with foundation depths ranging from 22 to 25 meters. So for the towers, 20 by 20 meter raft foundations were considered, whereas 3 by 3 meter isolated foundations were planned for the extended basements. The soil below the foundation level generally consists of sandy silt of low average shear wave velocity from the SCPTu3 test was found to be 486 meters per second, based on the VS values taken from the foundation base up to the depth of influence of the foundation level, which, as per the new IS code, is 2 times the width of the foundation. So based on this weighted average shear wave velocity, the soil at the site is classified as site class C, according to table 4 of the IS 1893 code. Liquefaction susceptibility assessment. So we had done detailed liquefaction susceptibility assessment using CPT, SPT, and VS data. The groundwater level during our investigation was actually influenced by dewatering. Am I audible? And is my slide visible, sir?
Yes.
Okay, let's continue. So the project site falls in zone 4 with a design earthquake magnitude of 7.0. And according to table 1 of IS 1893 part 5, tall buildings are classified as important buildings. So important buildings that fall in zone 4 are assigned a design return period of 975 years, which corresponds to a PGA of 0.28 G. With this information, we did the liquefaction susceptibility assessment using the IS 1893 Part 1 2016 as well as IS 1893 Part 1 2025. In the IS 1893-2016 code, the earthquake magnitude is 7, PGA is 0.24 G for zone 4, and factor of safety against liquefaction is equal to 1. And we found that based on SPT, CPTu, and shear wave velocity, there was no liquefaction potential at the site. The new IS code with a PGA of 0.28 G and a factor of safety of 1.2 for liquefaction triggering criterion also indicates no liquefaction potential for the SPT and the shear wave velocity based methods. For the CPTu based method, what we found is when we use the correlation to calculate the fines content, it's predicting liquefaction susceptibility between 4 to 10.5 meter depth, indicating a liquefaction potential index of 9.7 and a high risk of liquefaction. But when we used the actual measured fines content from the boreholes and laboratory grain size analysis, we found that the liquefaction susceptibility at the site was now much lower, with a lower LPI value and low risk of liquefaction, indicating better agreement with the SPT and the shear wave velocity methods. So when we plotted the fines content that we get from the correlation, which is the orange line, versus the measured fines content from borehole data, we see that there is a significant mismatch between the two across the depth. And this contributed to the different outcomes in the liquefaction susceptibility analysis. Also, when we plot the fitting parameter in the equation for the fines content versus depth, we see that the default value in the IS code is minus 0.07, which is the orange line. But when we back calculated the value for this fitting parameter based on the actual fines content, we see that it varies with depth, ranging from about plus 0.2 in the upper sandy silt layer and decreasing to about minus 0.5 to minus 0.6 in the lower silty fine sand layer. So what this indicates is that sometimes site-specific calibration of this fitting parameter may be required to get realistic assessments of liquefaction susceptibility assessment. This is just a graphical presentation of the CRR versus depth. So the orange line that you see is the cyclic stress ratio, and the pink purple line is the cyclic resistance ratio. So the 2016 code predicts no liquefaction potential. In the 2025 code, when we use the fines content from the correlation, it is predicting liquefaction susceptibility in this zone. But when we used the actual fines content from the borehole, then the liquefaction potential significantly decreased, which was in alignment with the SPT and the shear wave velocity methods. So quickly, the key takeaways. So according to IS 2016, for zone 4 with these input parameters, no liquefaction potential according to SPT, CPT, and shear wave velocity. In the 2025 code, for zone 4, with similar parameters, slightly higher PGA, factor of safety against liquefaction now upgraded to 1.2. SPT NVS is no liquefaction potential. CPT-based method with the estimated fines content predicts liquefaction to 10.5 meter depth. But when we use the actual fines content, the CPT-based method also indicated no liquefaction potential. So the key takeaway is that the CPT-based method in the new IS code is sensitive to the fines content, which is something we have to keep in mind. Site-specific calibration of the fitting parameter may be required on a project-by-project basis. And the default value of minus 0.07 suggested in the IS code may not suffice for all cases. Moving to case study number 2, which is a wind turbine in Kutch, Gujarat. So I'll quickly go through this slide. So as we know, wind energy is a national priority in India, and we want to expand our renewable energy goals. This includes the construction of onshore wind turbines in different parts of India. Key turbine specifications 5.2 megawatts of electricity per turbine. Rotor diameter is 160 meters and a tip height of 200 meters. The scope of work in Kutch, Gujarat included 300 plus wind turbine generators. At each wind turbine, the scope of the work included one borehole, one cross-hole seismic test, and one CPTu, all to 25-meter depth. Site stratigraphy, we can see a reasonable match between the stratigraphy from borehole data as well as the CPTu interpreted stratigraphy with minor variations in the layer thickness. The upper stratum from the ground surface to about 7.5 meters consists of medium stiff clayey silt with low SPTN values. That is underlain by non-plastic loose to medium dense sandy silt to 14-meter depth, and which is subsequently underlain by medium dense to dense silty sand to 25-meter depth with increasing SPTN values with depth. Groundwater was encountered at a depth of 3 meters, so shallow water level at this site. In terms of gradation and plasticity, so in the upper half of the soil profile, we see higher fines content with the presence of 20 to 25% of clay, with a liquid limit of about 35 to 40%, plasticity index of 20%, water content close to the plastic limit. As we go deeper in the soil profile, we see that the clay percentage drops to practically zero, resulting in a decrease in the fines content and an increase in the sand percentage. CPTu results, again, similar plots of cone resistance with depth, sleeve friction, pore pressure, and the CPT interpreted soil behavior type, indicating the presence of sandy silt and silty fine sand material down to 17-meter depth. Again, similar to case study number 1, CPTu interpreted parameters are in good agreement with laboratory measured values for each of these parameters. Similarly, we can see based on relative density that the relative density is about 40 to 50%. So in the loose to medium dense kind of a range, so susceptible to liquefaction. The CPT interpreted shear wave velocity was in good agreement with the measured VS from the cross-hole seismic test data. And this also translates to a good match in the small strain shear modulus, G0. So for the liquefaction susceptibility assessment, so this project falls in earthquake zone 6 as per the new IS code with magnitude 8.0. Now, given that onshore wind turbines are critical energy generation infrastructure whose failure can cause economic loss and power grid disruption, these structures are classified as important industrial structures as per Part 4 of IS 1893. So for important structures in earthquake zone 6, the design return period is 975 years with a PGA of 0.6 G. So with this input data, we did the liquefaction susceptibility assessment using SPT comparison. So on the left-hand side, you can see IS 1893-2016. Right-hand side is the 2025 code. And then these are plots of CSR and CRR. The orange line is the cyclic stress ratio representing the seismic demand, and the blue line is the cyclic resistance ratio. So the depth where the CRR is less than the CSR is where you have liquefaction occurring with a factor of safety less than 1. So according to the previous code, we see that the depth to liquefaction is about 15 meters. But when we do the analysis with the new IS code, with the updated earthquake magnitudes and PGAs, the depth to liquefaction increases to about 18.5 meters, representing a 23% increase in the depth to liquefaction. So what does that mean from a practical standpoint? It means that your ground improvement has to extend to deeper depths, resulting in proper investment in ground improvement techniques and associated cost. VS-based liquefaction susceptibility assessment. So in the 2016 code, depth to liquefaction was 21 meters, whereas in the new IS 2025 code, it increases to 22.5 meters, representing a 7% increase in the depth to liquefaction. CPT-based method between the previous code and the new code was more or less similar, and the reason for this was possibly due to the presence of non-liquefiable clay soil below a depth of 17 meters with a SBTN index IC greater than 2.6. So considering the liquefaction analysis, we had suggested ground improvement by stone columns, 800 to 1000 millimeter diameter vibrostone columns extending to about 24.5 meter depth. So at least 2 meters into non-liquefiable strata, with a triangular installation grid and a column spacing of about 2 to 3.5 meters, supplemented by peripheral rows of columns for lateral confinement. 500 millimeter thick compacted gravel blanket was suggested over the column heads in order to distribute the load uniformly from the WTG foundation to the improved ground. The primary objective of this intervention was to achieve a target safe bearing capacity of 180 to 200 kPa. And to verify the effectiveness of the ground improvement, we had suggested post-GI CPTu soundings 20 to 25 days after the installation of the stone columns. So summarizing the liquefaction analysis results, so based on the IS 1893-2016 code, we see that SPT, the depth to liquefaction is of the order of 15 to 21 meters across the three methods. With the new IS code and the enhanced earthquake magnitude and PGA values, the depth to liquefaction increases by 1.5 to 3 meters. Now, another finding in this project was the significant time savings that we were able to achieve with the use of CPTUs compared to boreholes. So for the total number of wind turbines that we had here, so 263 numbers of wind turbines, the total running meters of investigation was 6,575 meters. So if we take 5 SPT drill rigs and 5 CPTU rigs planned, with an average productivity of 10 running meters per rig per day for boreholes, or in the case of CPTu, 2 CPTUs per day. The estimated time duration for planning and mobilization was 15 days for boreholes compared to just 7 days for the CPTu. Testing, including sampling and laboratory testing for boreholes, was significantly higher, 161 days, as compared to CPTu, which was only 26 days. And preparation and submission of the draft final report was also much faster with the CPTu. So the overall saving in time that we could achieve by doing CPTu was almost 80% and at a lower cost as compared to boreholes. So for the final case study, I will hand it over to Ravi sir to conclude the presentation. Over to you, sir. Ravi sir, do you want to take over? Could you share your screen, sir?
Are you not able to see my screen? I'll share my screen again.
Yeah.
Can you see my screen now?
Yes, sir.
Oh, you can? Can you hear me also?
Yes, sir.
So this third case study is a bridge across the. This is the Palasbari.
Ravi, sir,
Huh?
sorry to
Come
interrupt,
again?
sir. Could you please click on, sorry to interrupt, could you please click on the hide button on the
Yeah.
tab at
Yeah.
the bottom? Okay, thank you, sir.
So across Brahmaputra, this is the bridge, Palasbari Suarkuchi bridge. This is the bridge alignment here. So this is over the Brahmaputra, connecting Palasbari to Sualkuchi in near Guwahati. So the bridge details here. This is a 4-lane PSC bridge with multi-span extra dosed units. Length is 3.6 kilometers with a width of 28 meters. 216-meter long viaducts on either side. It's a 864-meter long wetland viaduct. The total project length is 12.2 kilometers. So starts on NH17 from Kaita Siddhi on the south bank and crosses the Brahmaputra, terminates at Bongasor Sualkuchi Road on the north bank here. So this is the north bank here and this is the south bank. So the scope of work, we did 5 static cone penetration tests along the alignment to 40-meter depth to evaluate the stratigraphy to determine the geotechnical parameters, and the geotechnical analysis and report was based on the field data of the boreholes and then the SCPT seismic cone data also. So you can see the test being done along this alignment. So this is the alignment of the project plotted on a Google map. So the CPT results, you can see the interpreted values. There are the 4 CPTs which have been, you're getting the soil stratigraphy here, the top layers, you're getting sand, and then you have clay layers in between, and then below 7 meters again you have sand. So mostly it is sand with some clay layers in this zone. So the shear wave velocities, which were measured from the seismic cone penetration test, these are being compared here with the CPT, the shear wave velocity interpreted from the CPT data itself. So the solid line is what was calculated using the Robertson's correlations for the shear wave velocity. You can see there is a very good match with the data of the seismic cone, which is done at every 1 meter depth. So the liquefaction susceptibility assessment here, because the project site falls in earthquake zone 6, so magnitude 8.0. It's a critical bridge because it is more than 1 kilometer length, and Brahmaputra, as you know, is a perennial river, and alternate routes not easily available, although there is a long alternate route available. So design return period and PGA, these are taken as 2475 years and 0.75 G for the critical bridges as per the IS code. So you can see a comparison of the CSR and CRR plot based on 2016 and 2025. From the 2016, you get liquefaction from 6 to 9 meter depth, whereas if you will go for the do analysis as per the new code, there is around 5.5 to almost 11 meters. There is liquefaction. This means an increase of 22% in the depth of liquefaction. This is just physically, graphically plotted results of the CSR and CRR. The VS-based liquefaction analysis, here this is showing it increases from 7 meters to 8 meters. So that was based on the CPT, and this is based on the VS. So there's a 14% increase. So you can see a comparison here from SPT. You have 9 meters as per the earlier code, and VS gives me 7 meters, whereas the new code, it ranges from 8 to 11 meters. So depth of the liquefaction increases by 1 to 2 meters if you were to use the new code. So with this, I come to the conclusion of this presentation. IS 1893-2025 introduces a more realistic seismic hazard model with updated earthquake zone maps and a shift to VS-based site classification. Geophysical testing for shear wave velocity is now mandatory for site class determination, especially for critical and important structures. Liquefaction analysis uses design earthquake shaking and higher return periods to ensure site stability, emphasizing a responsible seismic design. Seismic safety is now very important, and particularly for important structures, the seismic safety assessment has been increased, particularly hospitals, bridges, etc. They now have a higher return periods and associated PGA values. So the assessment, liquefaction susceptibility assessment is now aligned to modern methods such as Bolanger and Idris 2014 and CPT-based approach and VS method. So we presented 3 cases from Gurgaon, Kutch and Guwahati to demonstrate the applicability of the code for liquefaction susceptibility. You can see in each of the cases there are substantial implications, and we have to be very careful in interpreting the depth of liquefaction. There is a government notification which says that the new code, which has been implemented from 3rd November, but to facilitate designers, the earlier code can continue to be used up to 3rd May 2026. So it gives you a 6-month window to transition. That is the impact of the code. So designers who can complete their design well before the planned date, they may use the old code, but then must be aware that the new code is more responsive to seismic events. Thank you very much. Welcome questions. Thank you. I have some questions in the chat box. Abhishek, would you like to reply to these? For shear wave velocity, VS can be used through empirical correlations, or is in situ testing compulsory? That's the question. This is from Mr. Manoj Kumar.
Thank you for the question. For shear wave velocity, as stated in the IS code, direct measurements of shear wave velocity are always preferred and better as compared to correlated values. And also for site class assessment, the code says it's important to do the geophysical testing to get the measured shear wave velocity values.
Thank you. I hope Mr. Manoj is clear. I have Mr. Pradeep Verma's question. Can you explain overburden correction CN in the new code? Because calculating CN, we need M, and calculating M, we need N60 CS.
Yes. Thank you for the question.
Yeah. And for
I
that, you
think,
need N160. Yes.
yes, there could be an iterative sequence that is involved here. So, based on the way the equations are defined, you would have to calculate each of these parameters accordingly. Let's see. I'll have to refer back to those equations which
It
are given
also
in the.
emphasizes on the fact that you need to measure the energy transfer.
Yes, use of an automatic trip hammer when you do the SPT along with the SPT energy measurement becomes very important.
I have Tanmay Gupta, an observation on slide 47. There is a typo error in the IS code for calculation of MSF max. The correct equation you should refer to Bolanger and Idris.
Yes, thank you for that observation. We had also seen the same, and we had uh, identified other typos as well in the IS code, and we compiled, made a list of them, and uh, plan to submit that to BIS for further consideration. But by stating where the equations come from, the audience can refer to the original publication, which is Bollinger and Idris, to get the correct equations.
Thank you, Abhishek. Atif Ahmed says, in hilly terrains such as Uttarakhand, where earthquakes primarily trigger landslides, do you see a scope within IS 1893-2005 to explicitly link seismic ground motion parameters with slope stability?
Slope stability analysis. In IS 1893 Part 1, 2025, at least, I am not 100% sure if the code talks about how to do a slope stability analysis from a seismic standpoint. The code focuses more on liquefaction susceptibility assessment, at least in Part 1.
I do think there is a scope for this, and researchers should work on this. And maybe we have some new guidelines coming up soon. Tanmay Gupta has a query. If we conduct SPT as per IS 2131, IS 1893 asks us to take C60 equal to 1. Could you elaborate on this clause, as if we use C60 equal to 1, the correction factors become irrelevant?
I can take this actually. Tanmay, I think this is another typo in 1893, and Bill pointed out it's not C60. There is no such thing as C60. I think they meant C sub E, which is the energy correction factor should be taken as 1. You still have to take the other 4 correction factors. What the clause clearly says is if you are carrying out SPT as per 2131 to 2025, and if your energy delivered is roughly 60%, then obviously that means your EC sub E is 1. But the other 4 correction factors still need to be taken.
Thank you, Saurabh, for that. JB Asif, I think. So, for tall structures, critical and special on rock, given the clear rock condition, is it still mandatory to perform VS testing for site classification, or can we rely on rock to treat it as a fixed base?
No, I think if your foundation is resting on rock, then you need not carry out VS testing. Code is quite clear about that. The depth to which shear velocity is to be conducted is only up to top of bedrock or bottom of socket. If your structure is resting on rock socketed piles, then shear velocity testing, as I understand, has to be carried out up to the top of bedrock, or rather up to bottom of socket. So that is what the code.
Yes.
Thank you, Saurabh. Maheshwari is asking whether overburden correction factor depends on corrected N. Please clarify how it can be accounted.
So if we start from the field measured SPTN value, you first apply your 4 correction factors to the raw SPTN value, which is hammer energy, rod length, borehole diameter, and sample liner. After applying these correction factors, you get what is called N60 as per the IS code. Now to this N60, if you apply the overburden correction factor Cn, basically it's a ratio of a vertical effective stress normalized to a reference stress of 100 kPa. You then get N160 to use in the liquefaction susceptibility analysis. I hope that answers your question.
At what Pranti Ghosh is asking at what condition liquefaction is considered not applicable? Saurabh had mentioned,
I
of course, if
imagine
there
you
is
mean
rock
this.
formation, it would definitely, you need not do it. And maybe you want to add regarding the factor of safety greater than 1.4.
Yes.
So if the factor of safety against liquefaction is greater than 1.4, then it is not applicable. It won't liquefy. Swapnil, hello Swapnil. Is asking to suggest to present a calculation illustration for an assessment based on the 2025 code. It's we have already gone more than 1.5 hours. These manual calculations would take a much more longer time. So, Apnil, if you can do the calculations, maybe we could have a look at it. Pranti Ghosh is asking when we are calculated liquefaction as per IS 1893 2025, that time after putting N value 25 to 28, sudden jump N160S. That's what I want to know. Consideration of value for N value.
I think Ravi sir is having Abhishek. We'll take the questions as they come.
Yeah. Pranti Ghosh, I don't understand exactly. Yes, you have to change from the measured N value to N160, whatever changes it occur in the measured N value, then the corrected value after N160, then you should do your liquefaction analysis as per that. Also, as per site condition, we find, I think you mean heterogeneous soil. In that case, any reference solution for N value? Again, I don't understand your question, Abhishek. Sorry, Pranti.
Okay, so let's quickly take. I think Ravi sir is also having network issues. So the Tanmay, no comments on this question. I think we can discuss this separately since this is not relevant to the topic at hand. Yes. The next question, Abhishek, is can you tell if shear wave velocity is greater than 220 meter per second, the correction value according to fineness is coming out to be negative? Correct. If the shear wave velocity is more than 220, this is correct. I think this is a good question by Annie. Yes, I think there is an issue we had observed that if your shear wave velocity is greater than 220, yes, the correction factor comes out to be negative. We are also still trying to clarify this. We don't really have an answer for you right now. That's an excellent observation, and we will get back to you separately on this, please. All right, next question is next question. Abhishek, maybe share your screen, please, so we can see the questions. I don't know.
Let me see.
Correct. This is the same thing. We can go ahead. Next question. All right. I think we are done with questions as far as I can see.
There is one question
I do
on
request
MASW.
if anyone has further questions, please drop us an email or give us a call. And I think, Abhishek, if you can share your last slide, audience can note down our contact details. And I think we can close this. Yeah. Sorry, sir. Yes, there's one more question. You have by Mr. Karthik. Sorry, I missed this. Thank you for informative lecture. Now in your lecture, you have thrown light on MASW, CPT, and whether still SPT needed when such advanced technology is available. $1 million question, Mr. Karthik. Short answer, yes. I think SPT still has its own benefit. I don't think it can be eliminated altogether. Although maybe a transition from conventional geotechnics alone to a mix of conventional and advanced geotechnics seems to be, seems to be where we are headed as an industry. But for the time being, I would not recommend replacing or eliminating SPT completely, except in certain specific conditions only. All right, cool. I think we can close. Thank you very much, Professor Ravi Sundaram and Dr. Abhishek. And thank you everyone for joining this webinar. We look forward to our next interaction. Thank you.
Thank you very much. It was a very useful interaction. There are any further questions, you may reach out to us. Thank you. Manju, you are muted.
Thank you, sir, for addressing the question and sharing your insights. Once again, thank you for joining us today. We look forward to your participation in our future technical sessions. Have a wonderful day. Thank you.
Thank you very much. Yeah. We're now closing this webinar.